In order to properly do a partial fraction expansion, the degree of the numerator polynomial must be less than the degree of the denominator polynomial. So what do we do when we have the degrees of the polynomials are equal? Well, let's see what we can do with this example. We have I'm going to assume that the order of the numerator and order of the denominator are the same. And here I have the function f of s, and f is equal to 6s squared plus 3s plus 2, which is the numerator, divided by 2s squared plus 14s plus 20, the denominator. So both the numerator and the denominator are second order polynomials. So what I do is I do a polynomial division. So I go through this exercise, which we have spent quite a bit of time on. So we go through the exercise dividing the denominator into the numerator, and we come out with the following. Okay, it's 3, and then this is the remainder. Notice it's 0 times s squared minus 39s plus 58. I mean, one way then of writing this, 3 with this remainder, is actually how we would do it with real numbers. We say that it's equal to 3, and the remainder is 39s minus 58 divided by um, the, uh, the denominator, by the fraction, by the expression by which we are doing the division. That is 2s squared plus 14s plus 20. So we have negative 39s minus 58 divided by 2s squared plus 14s plus 20. So this is how we write the remainder here. So after doing the polynomial division, our expression for f of s looks like this right here. And this I'm writing up here on the top, right up here. Okay, so let's do the partial fraction expansion for this expression right in here. First thing I do is notice that the denominator is divisible by 2. Every term in the denominator, every coefficient is divisible by 2. So I factor out a half to simplify this expression. The s squared, now a term in the denominator, becomes s squared, okay, plus 7s, that's not 75, it's 7s, s squared plus 7s plus 10. Now the denominator, s squared plus 7s plus 10, factors into s plus 5 times s plus 2. Okay, s plus 5 times s plus 2. So that means that our partial fraction expansion is going to look something like this here. F of s is equal to 3 plus 1/2, and the partial fraction expansion will be a divided by s plus 5 plus b divided by s plus 2. So now I implement my procedure for finding the coefficients a and b. And I've skipped a step here, and so you'll have to work with me. I say that a is equal to this whole thing, but multiplied now by s plus 5. So this whole thing multiplied by s plus 5 gives me this divided by s plus 2, because I've multiplied by the s plus 5 and the s plus 5s have canceled. So this is this whole expression multiplied, this whole expression right here multiplied by s plus 5. And then I take this expression that I get and I evaluate it at s equal negative 5. So my expression multiplied by s plus 5 evaluated at s equal negative 5. When I put in s equal negative 5 here, I get 195 minus 58 divided by negative 5 plus 2, which is negative 3. And then that simplifies to negative 137 over 3. So that's A. B, in a similar fashion, B is this whole thing, except multiplied by s plus 2, evaluated at s equal negative 2. So this whole thing multiplied by s plus 2 is this expression right here, and I'm going to evaluate this at negative 2. When I do that, I get Negative 2 times negative 39, which is negative 78, minus 58, okay, divided by 3, because negative 2 plus 5 is 3, or I get 20 divided by 3. So this is B. So I now have my expressions for A and B. A is equal to this, and B is equal to this. So I can plug those values for A and B back up into this expression right up here. Plug those in for A and B right up here. And when I do that, I get this expression shown down here. F of S is equal to 3, okay? And then 137 divided by 3 multiplied by a half gives me 137 divided by 6, okay, times 1 over S plus 5, that's here, plus 1 half times B, which is 20 divided by 3 times 1 half, that's 20 divided by 6. 20 divided by 6, though, cancels into 10 divided by 3, so I get 10 divided by 3 times 1 over S plus 2. So this then is the partial fraction expansion for my expression for f of s given right up here. Until next time.